All right, folks. Sorry I'm late. Listen, a couple things. We're gonna move on into chapter 5 right now in just a couple minutes, and then also there will be a quiz on chapter 5 this coming Tuesday. So it'll be at the beginning of class like we usually do. Okay, 10 questions. Just read through that chapter. It is kind of a tough chapter, so I would read through it today maybe, and then see how you feel about it, and then spend a little extra time if you need. So it's one of our tougher chapters. There's just sort of some difficult ideas in it, and then also neurons and stuff like that, which I don't know. Y'all know much about neurons and how they work? All right, we're gonna look into it. We'll learn about it. But anyway, so a lot of the stuff at the very beginning anyway, is probably stuff you've had before, high school. Just the basics of charge, what is charge, that sort of thing, how charge responds. And we'll look later at how the body responds to charges, but for now we're just going to look at charges and they uh, how they respond to one another. So the title of this chapter is Electrical Properties and Cell Potential. Now let me just sort of give you a quick little preview because we're going to have three big topics and students often confuse them. We're going to look at electrical forces, electrical fields, and electrical potentials. And those are all related to one another, but they're also different. So we're going to look at forces, fields, and potential. And when we're learning about how electricity is used in the body to transmit information, like in your nerve cells, these will become important. We'll talk about all three of these actually. So electrical forces, I'm going to repeat this as we go along, but just sort of a little preview of what we're going to see. Electrical forces is just the force between two charges. Like for example, if I have a positive charge and if I have a negative charge, these two charges are going to feel a force between them. And we'll talk about the law that governs that. It's called Coulomb's law. If I have two charges, they're either going to be attracted to one another if they're opposite charges, or they be repelled if they're like charges. The field is a force per charge. All right, so if I have an electric field, I can draw it with some lines, and we'll see electric fields and how they operate in nerve cells later, probably on Monday, or Tuesday rather. But the electric field is a force per unit charge, and so if I have an electric field that has been produced in some way, and it's going to be produced by other charges, but if I place a charge into this electric field, it's going to feel a force. And we describe the force that it feels by the electric field. As a result, so let me give you some units here to keep you straight. Charges are in units of coulombs. You might be familiar with that. You've probably dealt with charges in one of your classes, chemistry or physical science in high school, but charges are measured in coulombs. You've heard that term before, coulombs? Yeah, maybe you have, maybe you haven't. Anyway, that's how we measure. It's one of our basic SI units. So we've already talked about those basic SI units for mass, length, and time. Charge is also one of those basic SI units. Now force, the force is in newtons, and so for the field, we're going to have units of newtons per coulomb. Potential is something that's even a little more difficult to understand than fields. Potential is going to be an energy per charge. So the units for this, energy, of course, is in joules. Charge is in coulombs. So it's going to be joules per coulomb. Or usually what we write the units for potential is going to be in volts. And it says that if I have an area that has a certain potential, that means that charges in that potential will have a certain energy per their unit charge. All right, so this very much is related to energy, whereas this is related to force per unit charge, and then our electrical forces, all of this is derived actually from our expression for our electrical forces. Forces, fields are forces per charge, measured in newtons per coulomb, and then potential, electric potential, is going to be energy per charge, measured in volts or joules per coulomb. Particularly the potential we'll get into. You've probably heard of if you studied. Actually, I don't study neurons at all in anatomy. cell potential or membrane potential. None of that rings a bell to you. Some of you it might, but we'll get into it later in this chapter, at least on a surface level. It can get quite complex as you go deeper into it. Okay, so let's just sort of talk about the basic properties of charges now. Stuff that you're probably familiar with. Electric charge. It's a fundamental property of matter. And you can think of it akin to mass. That mass is a fundamental property of matter. Charge is also a fundamental property of matter. We all have charges. Every type of matter has charges, is made up of charges. Sometimes the net sum of all those charges is going to be neutral, like we're generally neutral in charge because we have equal numbers of positive and negative charges. But all matter has charges. So you can think of it as just this fundamental property of matter like mass. We have what we call the fundamental unit of charge. And the fundamental unit of charge, which we call E, 1E, this has a value that's equal to 1.6 times 10 to the minus 19 coulombs. Don't bother memorizing that number, but what you do need to know is that this is the most fundamental, or the smallest value for charge that we can have. Because this is the charge of a what? This value, if you've seen it before. What is this the charge of? No? It's the charge of a proton, or it's the charge of an electron. So this is the value of the charge for a proton and an electron. A proton has a charge of plus 1e, and an electron, which is negatively charged, has a charge of minus 1e. All right, or minus 1.6 times 10 to the minus 19. It is the fundamental unit of charge. By the way, for a neutron, which is so named because it's neutrally charged, it has a net charge of 0e. So it has no net charge at all. All right. All atoms have charge, but most are neutral. Right, this is third grade science. If we have 3 protons, is that lithium, I think, with 3 protons? I'm right about that. I think it is lithium. All right, if I have 3 electrons, then I'll have 3 protons, I'll have 3 electrons. And so we would say that substance, that atom, is neutrally charged. It has equal numbers of positive and negative charges. However, you can have some ions. You do need to know what these are called. Cations, positively charged. So for example, we would have 3 protons, but then maybe just 2 electrons. And then anions are negatively charged. So for example, we might have 3 protons, but we'd have 4 electrons orbiting around that nucleus. Okay? So cations and anions, just know those terms, what they mean. I don't have a good way to remember it. I always think of an as kind of a negative term, but like asymptotic, A generally means against. So I don't know if that's where the root of the word comes from. Oh, there you go. Yeah, so cations has a plus in the middle. Good. All right. So cations and anions. And always atoms become charged by removing or adding an electron. All right. The reason is that protons are very tightly bound in the nucleus, and so it's very difficult to actually remove a proton from an atom. And so if you have a cation, it's not it's positively charged not because you've added a proton, but because you've stripped away an electron. And similarly, for an anion, it's not negative because you've removed a proton, but because you've added an electron. All right, so these are positive or negative based on what you do with the electrons. All right, let's go back to one other thing. One of the results of this fundamental unit of charge, that all charge is made up of this, is that you can only have particular quantities of charge. That is to say that charge is quantized. And so, for example, if I have 2 protons, my charge is going to be 3.2 times 10 to the minus 19. If I have 3 protons, my charge is going to be 4.8 times 10 to the minus 19. However, I cannot have, say, 4.2 times 10 to the minus 19 coulombs. That just isn't allowed, because then that would mean that you have some portion of a proton, or if they're negatively charged, some portion of an electron. Charge is quantized, so it has to fall in these discrete quantities. 3.2, 4.8, 4 times this, 5 times this, 6 times this value. You follow what I'm saying? You can only have values for the charge that are equal to plus or minus 1e, plus or minus 2e, plus or minus 3e, and on, 4e, 5e, 6e. Charge is quantized. It only comes in particular quantities. Okay, so let's look at the electric force. This is described by Coulomb's law. Oh, no, I want to show you a couple things just before we move on. So you can do some stuff with charges. Unfortunately, they don't work very well on humid days, especially like today, so this might not work at all. And later, I'll bring in our Van de Graaff generator when we get to this, and we'll be able to see it a lot better. But you can do some stuff with charges where, like if I have some paper here, I don't know, is paper an insulator or a conductor? That is, does paper allow for the transmission of electricity, or does it not? Is it an insulator or is it a conductor? It's an insulator. Paper's a pretty good insulator. That means that charges won't move around very much on a piece of paper, but we can actually attract them. So if I have certain charges, so I'm going to put some charges on this piece of PVC pipe. This is just like an old nasty sock that I washed. It's clean. It's not dirty. Put some charges on here. I can actually hear it crackling a little bit, but it might not work. So let's see. Yeah, you can sort of see. See the little pieces of paper jumping around? I have a few pieces stuck on here. You'll see that up front. I'm sorry you can't see in the back. That's because when I get these charges onto here, there's this attraction between the charges that are on the pipe. So I have this piece of PVC pipe. I put these negative charges onto the pipe, and then I have the paper here. Now the paper is neutrally charged, so it has equal numbers of positive and negative charges. And so what the paper does, the charges won't move around on the paper because it's an insulator, but the paper will orient itself so that the positive charges are here and the negative charges are here. And that's what causes it to attract to the charged rod. This usually works a little bit better with balloons, if you have any balloons at home. See if I can blow this up. I used to smoke like a bunch of years ago. I don't know if y'all smoke, but it's really bad for you. So I probably couldn't even blow up a balloon like 10 years ago. Ah, this one has a hole in it. It's got a big old hole in it. Cheap balloon, dollar store. Oh, this one has a hole in it too. Well, shoot. I'm sorry. I'll bring some more balloons later. Okay. I had pulled out 2 balloons earlier, and one of them had a hole in it, but the other one didn't. I said, well, I'll just get 2 balloons. Certainly out of 2 balloons, I'll get one that'll work. But sorry. It was amazing what I was going to show you, but sorry that you didn't get to see it. Now, as I said, in humid conditions, especially like today, these sort of things don't really work very well. The reason is that water is a polar molecule. And if you have a water droplet, it's going to be slightly more charged on one side than the other. So the water molecule will actually be positively charged on one side and negatively charged on the other side. That's what it means that it's a polar molecule. It's slightly more negative or positive on one side or other of the molecule. And because of that, the water molecule is able to strip away charges. So the water molecule feels attracted to these charges, and these little negative charges will jump over and stick to the water molecule because it's a polar molecule. So the water will take away charges, so to speak. These sorts of static electricity type experiments don't work very well. But later on, probably Thursday or so. Oh, wait, no, we don't have class on Thursday, do we? Do we have class on Thursday? That's unfortunate. Right. I'm available if y'all want to have class. Yeah, next week is beginning. Yeah, I don't know why they did that. That's not normal, right? Is that normal to have Thursday off? It is. All right. So let's look at the electric force. Probably what that means for us guys is that this chapter, only a portion of it will be on the test. So I'll see. I'll let you know. I guess on Tuesday because we have our test. You know when we have our test? Is it the following Tuesday or the following Thursday? Is that following Tuesday? Okay. Let me just show you real quick. Yeah, so we have a test on the 5th. All right. Yes. Yeah, the first day back. Oh, the second day back. Because you have Monday. And then we come back. That's right. 4 and 5, right? All of 4 and just a portion of chapter 5. Right, so let's look at electric forces. Um, electric forces are between two charges. So let's say, for example, I have a positive charge, I have a negative charge. Let's say that they're separated by a distance d. They feel a force that is attractive. They have one force in this direction, another force in this direction. I'll call this one Q1. I'll call this charge Q2. So this force will be the force on particle 1 due to particle 2. And then this force will be the force on particle 2 due to particle 1. Now, we describe these forces mathematically by Coulomb's law. Coulomb's law, which is just determined experimentally, shows us that the force is equal to K, this is going to be a constant, I'll give it to you, times Q1, Q2 over R squared. All right, so here, Q are my charges. They're in coulombs. Sorry, not R, D squared over D squared. D is the distance. It's going to be in meters. And K is Coulomb's constant. You don't need to know what it is. You won't even have to do a calculation with this, but in case you ever see it, it's 9 times 10 to the 9th. And it's Newton meter squared per Coulomb squared. Right, so this is sort of the fundamental law that we use to describe forces between electrical charges, and it will also carry out that we'll describe our fields and our potentials. But basically, all of electricity derives itself from this law and how charges react to one another. That they're attracted, like the charges on the PVC pipe, and the negative charges, they were attracted to the paper, the charges on the paper, and caused them to stick together. It's a very fundamental law, describes the force between two charges. We had something similar before, I don't know if you remember, when we were talking about gravitation, we had Newton's universal law of gravitation, and it looked very similar to this. don't write this down, but I'll just give it to you for reference. It was just that F equals G M1 M2 over D squared. That was the force between masses. Again, don't write that down. But notice that these are very similar. That's because they're both spherically symmetric. All right, so that's Coulomb's law. Remember, like charges repel. So if I have two positive charges, they'll feel forces in this direction. Or two negative charges, they'll repel. And then opposite charges attract. So if I have a plus and a minus, these charges will be attracted to one another. If there are multiple charges, then you have multiple forces. So say, for example, let's say that I have a charge like this, positive charge. I have a negative charge up here, and then I have another positive charge over here. Now, there are going to be two forces that are acting on this charge. I want you to tell me, we'll do this as a quicker question, what is going to be the net force on this charge? And I'm going to show you a series of vectors, and I want you to tell me what is going to be the net force. Now remember, there are going to be two forces acting on this charge, so I want you to tell me what is the net force. Let's see, is it going to be here? That will be A. Will it be here? That'll be B. Here is A, B, C. Will it be here, or will it be here? We'll call this D, and we'll call this E. Now remember, there are two forces acting on this charge. What I want to know is which of these is the net force. So you have to add up those two vectors in your mind. Back to your vectors and think about how, if we have two or more vectors, how do we add them up? So let's try this and see how we do. All right, so go ahead and put in your answer. Which do you think? Have these two forces, what is going to be the net force between the net force that acts on this negatively charged particle? Let's think about this. Let's say that we have, y'all are sort of spread between a couple different answers. Let's say that I have, I don't know, an object right here, and I have a rope attached to it, and I have a guy pulling on that rope. And then I have another guy with another rope, say in this direction. And this guy's pulling on that rope. And they're both pulling with equal forces. All right? Which of these, or what is going to be the direction of the force, or the direction of the motion for this thing that they're trying to pull? Is it going to be towards this guy, or is it going to be towards this guy, or in some other direction? Right, it's going to be right down the middle, because they're both going to be pulling on it, and it's going to pull the object in this direction. And so the net force is going to be somewhere in between those two guys. So you can think of this as force vectors, that this guy is applying a force vector in this direction. This guy is applying a force vector in that direction. And so the sum is going to be right down the middle. All right. Oh no, y'all went the opposite direction. All right, I'll show you what you put. I'll give you the right answer. I'm going to stop this. 150. Okay, now D is the right answer. Look, I have two forces that are acting on this charge. I have one that's in this direction, in the direction of that force, that charge. I have another that's in this direction, in the direction of that charge. Huh? And then the net of those is going to be in between. Now what you needed to realize is that they are opposite charges, so I am going to have attractive forces between these two particles and these two particles. If you didn't consider that, then you might have gotten one of these other options if you thought that maybe they're repulsive and not attractive. But they are attractive forces, and so the sum of those forces will be right down the middle, or D is the sum of those forces. You can see a simple question like that with force vectors and how they relate to electric forces. But you need to consider, are they attractive forces or repulsive forces? Okay. Your book does a calculation. I'm just going to show you this. I'm not going to require you to do a calculation. Let me just show you, for example. Your book does a calculation between two carbon atoms, and a carbon atom has a charge of plus 6e. And so if you had two carbon atoms separated by a certain distance of 0.5 nanometers, then you could figure out what is the force between them. Again, I'm not going to ask you to calculate the force. You don't even have to use a calculator, right? But it is a useful thing to do if you're dealing with charges and you need to know what are the forces between them. And later we'll talk about forces and how they're related to, I said, the transport of charges in the body. But here, if we wanted to know this force between these two carbon atoms, I would have 9 times 10 to the 9th. That's our Coulomb's constant. And then our Q is going to be 6 times 1.6 times 10 to the minus 19. That's my Q1. And then my Q2 is going to be 6 times 1.6 times 10 to the minus 19. That's my Q2. And then I divide that by the distance squared, a half a nanometer. Let's see, do y'all know what nano is? What is nano in the metric system? It is 9. Awesome. Yeah, it's 10 to the minus 9. It looks a lot like 9, right? So it's 0.5 times 10 to the minus 9 meters. And then this is squared. All right, so if you calculate that, you can find the force, and that force turns out to be really small. It's like 3.3 times 10 to the minus 8 newtons. All right, you're not going to have to calculate forces, but just know that this is how this works. Now, what you will need to do is, given this expression, which is on your equation sheet, be able to tell me how the force changes as some of these variables change. So let's try this. So let's say you double Q. Or we'll call this Q1, we'll say this is Q2. What happens to the force if you double one of the charges, say Q1? Do I get 4 times the force, twice the force, the same force? Oh, that should be 2F. Half the force, or 1/4 of the force? What happens if I double Q1? If Q1 is what it is here, my force is F. What happens if I double Q1? What will happen to the force here? All right, just a few more seconds. Do another. I'll stop at I don't know, 30. Okay, good. He is right. If I double one of those charges, it's a linear relationship. So if I double Q1, I double F. Let's try a different one. Instead of doubling Q1, let's say that I double R. What happens to the force? If I separate the charges by a factor of 2, what happens to the force between them? Here what I'm doing is I'm doubling R. I want to know what happens to F. All right, I'll stop at 48. 48. Okay, good. E is right. If I double R, Since it's squared, it's an inverse square relationship. Since it's squared, I get a quarter of F. All right? So we do this because it's important to be able to look at an equation anytime you see an equation and not really just see a jumble of letters, but to see these relationships. Well, if I change the force, then it's going to change this. Or if I change Q, it changes this in this way. And so it is important. And often students, listen, Derek Muller, y'all know Derek Muller from Veritasium? You know the guy? He told me, if I met him right, he told me, did I show y'all the picture? He told me, actually, he told about 300 or 400 people, but I was there in the crowd. And he said that that often when, like, say a scientist looks at an equation, like Newton's law or whatever, F equals ma, that they see an old friend, and they want to take it and they want to go sit down with it and eat dinner or whatever with it. But then when a student sees an equation, they just see a jumble of letters, and it doesn't really make any sense. So I really want you to be able to look at an equation and sort of see the relationships that are going on, and not so much just seeing a jumble of letters, and begin thinking about, well, if I change this and that, then how does it affect these other things? So look at this as like an old friend that you'd want to take out with you for dinner or something. Can you do that? No. Okay, good. But you'll likely see some questions like this, where if you change the distance or you change the charge, then what happens to the force? All right? Oh, let's try another one. So what if I do both of these? What if I double Q1 and I double R? So what if I do both of these? What will happen to my force? I'm both doubling Q1 and I'm doubling R. So I am doing this and I'm doing this. So if I double Q1, I do that. I double R, I do that. So how does that affect the force? Ask your neighbor what they put, please, because about half of you are still missing it. Ask your neighbor. If they have something different, try to tell them. Okay, good. You're moving in the right direction. Just a few more seconds. I'll stop at 110. 110. Or a little better here. Okay, good. D is right. Because if I double the distance, since this is squared, I have this 2, and then I square it, I get a 4 in the denominator, and I get a 2 in the numerator. 2 over 4 is going to be a half. So my force will be half what it originally was. Okay. Let's look now at electric fields. Oh, wait, no. So our body uses electric forces. To move cations and ions around. Look, I'm going to start writing it like this with a big that up front. Does that help y'all? I love that, Marissa. That's great. I've never heard that before. To move cations and anions around. And we'll see later, it'll probably be on the next exam, but we'll see that for the nerve cells, that we'll use these electric forces to move potassium and sodium ions across the cell membrane in our nerve cells. All right, we can imagine that we have this structure. All right, let's say your book does a figure like this. Let's say that I have positive charges over here, negative charges over here. We're going to call this a capacitive structure. How do you spell that? A capacitive. Yeah, capacitive structure? I tell you that because later we're going to look at capacitors, and they will look a lot like this, so they won't be terribly unfamiliar. But it's a capacitive structure where you have charges on either side. So I have positive charges over here and negative charges over here. And again, we'll see with the nerve cell that we get very much a positive charge on one side and a negative charge on the other side, and that will cause for charges to move back and forth between this. So if I have, a positive charge here, what is the direction that it's going to feel a force? Is it going to feel a force that's up or down? It's going to feel a force that's down. And likewise, negative charges are going to feel a force that's up. So we'll look at these different charges and how these forces are used to move these cations and anions in between different spaces. All right. Let's go into electric fields. Remember, if electric force is measured in newtons, an electric field is really just an extension of the electric force, but it's going to be a force per unit charge. An electric field is a force per unit charge, or per charge. That's sort of the basic definition of an electric field. In fact, if you ever hear about fields in general, a field is a force per unit something. So sometimes we talk about gravitational fields. We didn't talk about it in this class because it's a little bit, it's not really part of this class, but the gravitational field is also a force, but a force per unit mass. So an electric field is a force per unit charge. We can describe it mathematically. E, we call it, is defined as the force over charge. This just means it's defined in this way. And so we say we have a charge right here. If I were to put another charge right here, it would feel a force. So a charge placed at this point would feel a force. And so since it would feel a force, we will say that there is an electric field here. The electric field isn't really something real. It's really just a mathematical tool that we make up to describe the force that a charge will feel at this point. Likewise, there's an electric field here. Is the electric field here going to be bigger or smaller than the electric field at this point? Think about it. Let me put that in terms of a clicker question. Let's say that this is point A and this is point B. Is the electric field at point A, is it bigger than the electric field at point B? Or is the electric field at point A smaller than the electric field at point B? This is going to be A and this is going to be B. Which of those is true? Is the electric field bigger at point A or is it smaller at point A? And now think about it now. Our electric field is a force per unit charge. So I can imagine a force here, or I can imagine a force here. So really the question that we're asking is, what is that force per unit charge that we'll feel at A or B? And then that'll tell us what the electric field does. Is the electric field bigger at A, or is it smaller at A? You're doing really well. Most of you have the right answer. Ask your neighbor. Your neighbor probably has the right answer if you're not sure. All right, I'm going to stop at 48. 48. Okay, B is right. Yeah, the electric field at A is smaller. Now, remember our Coulomb's law. And our Coulomb's law is really pretty fundamental to this. K, Q, Q over R squared. What happens if I go farther away from a charge to the force? If I increase R, what happens to F? It decreases, right? As I move charges farther apart, the electric force between them decreases. So my electric force is going to decrease as I move from here out. So since my electric field is just my force per unit charge, the electric field out here is going to be less than it is out here. That means that if I put a charge here, it's going to feel a smaller force than if I put the charge here. Okay? The electric field just describes the force that a charge would feel. It doesn't describe the force that it does feel, but a force that the charge would feel. So around this charge, we can describe the field. We usually draw them with lines. The electric field emanates outward, and all around this charge, that electric field exists. As you move further away from the charge, you get a smaller field. As you move closer into the charge, you get a bigger field. Field lines are often used in this way to describe electric fields or gravitational fields or whatever. The magnitude, remember, smaller out here, bigger out here. These sort of read like topographical maps. When lines on a topographical map are really close together, that means that you have what? A steeper grade or a shallower grade? You know, on a topographical map, if your lines are all really close together, we don't really have hills, but if you have lines really close together on a topographical map, what does that tell you about the hill? Is it going to be a really steep hill or a shallow hill? It's going to be really steep on a topographical map. In a similar way, when the lines are really close together, the electric field is big. When the lines are far apart, the electric fields are small. Okay, the direction of the field is the direction that a positive particle would feel if it was in that field. So to find the direction, I'm going to go down to the next page actually. Consider a positive particle at that position. And ask yourself, what is the direction of the force? And whatever the direction of the force, that will be the direction of the electric field. So imagine that I have a positive particle. There is an electric field that emanates outward from this positive particle. All right, I want to know what the direction is. So I imagine that there is another positive particle out here. Now that positive particle here will have a force in which direction? To the left or to the right? To the right, because two positive particles are going to repel one another. So this positive particle will feel a force in this direction, and so my electric field is going to be in that direction. Similarly, if I imagine my positive particle, say up here, it will feel a force in that direction. Up here, that direction. And so my electric field emanates outward. So to find the direction of my electric field, I just consider the direction that a positive particle would feel a force. And so the opposite of that is also true, that a positive particle will always feel a force in the direction of the electric field. You'll see how those are connected? A positive particle will always feel a force in the direction of the electric field. And again, we'll see that in the nerve cells and how the positive particles will follow the direction of the electric field. Let me write that, just make sure that writes clear. So positive particles feel a force in the direction of the electric field. All right, so you need to know that electric field is a force per unit charge. Right. Have a basic understanding of how these lines represent the magnitude and the direction. The direction of the field is just in the direction of the arrows. The magnitude, the strength of the electric field, has to do with how close the lines are. As I move further away from an electric field, because the force decreases, or excuse me, as I move farther away from a charge, because the distance increases and the force decreases, that means the electric field will also decrease. And then also this, that positive particles will feel a force in the direction of the electric field. The electric field, do a quick derivation, and you'll have this equation. Remember, the electric field is force over charge. That's K, Q, Q over D squared. divide that by charge, and I get an expression for the electric field, kq over d squared. That's on your equation sheet, but that just tells me what is the electric field, what is the force per unit charge at a certain distance from a charge. Okay, now let's look at electric potential energy. Can I go down from here? This is a difficult chapter. I don't know about y'all, but when I first sort of heard of these ideas, they were kind of confusing to me. So it might take you a little time reading through the chapters and thinking about electric fields, electric forces, electric potentials, and electric potential energies to really get them all sorted out straight in your mind. So I would go ahead and try to at least take a first look at the first half of Chapter 5 before the quiz on Tuesday. All right? And then, of course, you'll need to look at the second half, largely just neurons and how they work, and know the parts of the neuron and the basic principles behind them. All right, so let's look at electric potential energy, which will also come up when we're talking about nerve cells. There are a few takeaways here that'll be important for later, and I'll try to point those out. Okay, so potential energy, I'm going to abbreviate it as PE. Potential energy describes an object's capacity to do work. So for example, we talked about this in terms of gravitational potential energy. If I have an object here and I let it go, it exists. It has the capacity to do work, or it has the capacity for motion. So if I let it go, it has energy, and it falls. Okay. The same is true for charges. If I have two positive charges and I have them with a certain distance from one another, what happens if I let them go? Right, they split apart because they have this repulsive force. So in a very similar way that we had gravitational potential energy, we'll also have electric potential energy. Now, we can do sort of a loose derivation. I know that work is, gosh, what was our expression for work? Force times something. Do y'all remember? Yeah, force times distance. So my work is force times distance, or displacement. It is a force acted on over a certain distance. You have to have both of those in order to have work. Your book calls this U. So we're going to use U for potential energy. And it's equal to, our force is KQ over D squared. And since we have a D here, now our U, our potential energy, is going to be KQQ over D. Again, this is on your equation sheet. Let me just pull that up and show you. I just want to make sure that that is the case, too. You'll have it on the exam. Oh, I don't have Chapter 5 on here, but I will have Chapter 5. I'll get it on there for you. But you'll have all these expressions for the force, the electric field, and the electric potential energy, and then also electric potential as well. And you should be able to answer, you know, those type questions where if I change one value, what happens to the other values? All right, so that is my electric potential energy. Call it U. You can have either positive or negative. Potential energy. Notice that our charges can either be positive or negative here. Now with gravitational potential energy, you couldn't really have negative potential energy, but with electric potential energy, because you can either have repulsive or you can have attractive forces, then you can have positive or negative potential energy. So if you imagine you have two positive forces or two positive charges, they want to do what? If you let them go, they're going to repel from one another. And we would call that positive energy. Whereas if I have a positive and a negative charge, that would have negative energy. If I let them go, they would attract to one another. Okay? So it just comes about from the signs. So you can have positive or negative U because Q can be positive or it can be negative. Likewise, if I had two negative charges, what would the energy of those two be? Would they be positive or negative? If I had two negative charges, it would be what, Lanisha? No, I thought you said the answer. It would be positive, right, because a negative times a negative is going to be positive. All right, and they would fly away from one another, and we would call that positive potential energy. Okay, charges move in electric fields. Right, we've already established that. Now, when I have an electric field and I put a charge in it, it's going to move because it will feel a force when it's in an electric field. Generally, um, charges prefer to move in the direction of decreasing potential energy. You can think about this as like a hill. Say you have a hill or a mountain, and then I have a ball that's on it. What is the direction that the ball is going to move? Is it going to move so that it has more potential energy, or will it move so that it has less potential energy? That is it going to move spontaneously up, or is it going to move spontaneously down? What's it going to do? That was a question. Is it going to roll up the hill or down the hill? It's going to move down the hill because it's going to move to a place where it decreases its potential energy. And the same is true for charges, that they will move in the direction of decreasing energy, potential energy. So for example, if I have an area of high potential energy and I have an area of low potential energy over here, of a positive charge, it's going to move in that direction, from high potential energy to low potential energy. Or high, sorry, I should use this term, U, is what your book uses. But I'm using it in the same way as PE. Okay? Again, that'll be important because we'll talk about when we get into the cell how charges, anions and cations, will move from an area of high energy to lower energy as they're in the body. By the way, negative charges, not to muddy this up too much, but if I have a negative charge here, a negative charge will tend to move in the opposite direction as a positive charge. You might expect that because, positives and negatives, they sort of act differently. So a negative charge will move in the direction from low to high. Don't worry about that too much. I mean, just figure that generally charges, or positive charges, will move in the direction of decreasing potential energy. Okay? This is generally true. It's just for negative charges, it's going to be the opposite. Okay. Let's see, where are we? Now so that's potential energy, and that's going to be different from electric potential. So let's do a few clicker questions first. By the way, I did post on the website, and I sent you all a message about the, where are they? The concept test. I did put up the chapter 5. That's the ones I'm going to have here. I also put up chapter 6, which is going to be our next chapter. We'll have another chapter after that, knock on wood, hopefully. But I'm pretty sure that we will. If we don't, I'll probably split up the reading quizzes for that chapter into 2 pieces. But I'm pretty sure we'll get another chapter after that. And then I also have chapter 4. Did y'all print out these? Do you want me to go through and give you the answers? Do so, or just one of you has it? Can I wait till next time, or? Okay, next time I'll go through. If y'all want to do this, then I'll give you all the answers for them. We had them in class, but Morgan, if you want, I can come by right after class. I can show you if you want, or you can wait. Okay, so you can take those and print them out as you like, because the answers aren't on there, and so you might want them in class. Take those. Okay, now let's look at electric potential. Remember when I was a student, I always got electric, gosh, all these fields and potential energy and potential, they all look really similar, like the equations all look very similar, and they all sort of mean roughly the same thing. They're all taken from this Coulomb's law, and so it just took me a long time to really sort these out in my mind. And that might be true for you too. Electric potential. This is a measure, as I said in the very beginning, this is a measure of energy per charge. So it's very similar to our gravitational potential, or excuse me, our electric potential energy, which we just saw before. We can think of potential, we're going to use V as energy per charge. I'm going to call it U over Q. Right, this is our potential energy. So the electric potential is kind of akin to the fields and the forces. A field is a force per unit charge. In the same way, a potential is like to the potential energy. It is the potential energy per charge, or U over Q. So if I have a certain potential at a particular location, and I put a charge there, it will have a certain amount of energy. If it's a higher potential, it'll have more energy. If it's a smaller potential, it'll have less energy. Okay? So potential is the potential energy per charge. How much energy per unit charge does it have? Oh, sorry, we're going to do some clicker questions real quick. You know what I said? Sorry. Sorry, my kids are still sick. My girl, she's still running like 100-degree fever. It's been all week. My son was sick on Friday, and then he was sick up until yesterday, and then my daughter got sick a couple of days ago, and it's like she's been running really high fevers all week. She's better. She was joking around this morning. I left my tie on the bed because I was trying to wash the dishes or something. I just left my tie in the bed, and I come back, and I'm like, where's my blankety tie? I didn't say that. I said, where's my tie? And she had the blanket all pulled up to her chin, and she was giggling. She was in her bed. She was giggling. What are you laughing about? And I pulled the blanket down, and she had my tie all tied up around her neck. She had a pretty good knot in it. Okay, so a positively charged atom is called what? A cation, anion, pion, or a gluon. All right, I'll stop at 22. 22. Okay, awesome. A is right because of that thing. Right? Is that how y'all remember that? Because it has a plus sign in the middle? Hey, I just heard this one. I want to hear it. How many times do you have to tickle an octopus to make him laugh? Tentacles. 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 Eight. Eight tickles? I don't know what that is. All right. So it is a cation. Which of these is not a valid charge? Remember, the fundamental unit of charge is 1.6 times 10 to the minus 19. All right, I'll stop at 45. 45. Okay, C is right, because it would be 5.4, not 5.2. So this is one proton. This is three protons. This is somewhere between 3 and 4 protons, and you can't have a part of a proton. So this is not good. This is two what? Electrons, right? Because it's negative, and E is not right. So C is the right answer. Okay. Which of these is true? I'll stop at 42. 42. A is right. 1 and 2. The electric charge of the particles, remember this is K, Q, Q over distance squared. So the electric charge is relevant. And then also the distance between the particles is also relevant. Turns out that the radius of the particles doesn't really matter. That's just not relevant. Only the distance between the particles. And then also the mass of the particles. Well, that might affect how they move. It doesn't affect the force that they feel. By the way, if I had two particles with the same force, which would move faster? One with a bigger mass or a smaller mass? The smaller mass would accelerate at a greater rate. So let's try this one. All right, folks, so what am I doing to these charges? I'm moving them closer, or am I moving them farther apart? I'm moving them farther apart. So first of all, I just want to ask myself the question, is this force going to increase or is it going to decrease? It's going to decrease. As I move these charges farther apart, they will feel a lesser force. So it was feeling 12 newtons. So now it's going to feel not a bigger force, which I'll probably put this one, and not a bigger force here, and also not the same force. So it can't be C, D, or E, okay? Because I've moved them farther apart, and I know that my force is equal to K, Q, Q over R squared. So I'm increasing R. That means that my force has to decrease. It's an inverse relationship. And now the question is, which is it? Is it going to be A or B? I'm increasing R by a certain amount, by some factor. How does that affect my force? Well, ask your neighbor. Y'all still split, like between A and B. You're almost evenly split. Ask your neighbor and see what they put. Somebody you trust. All right, I'll stop at 225. 225. All right, we're still sort of, but you're a little better than you were before, but A is the right answer. Because if I double, what I'm doing is I'm doubling R. I'm going from 2 meters to 4 meters. So I've doubled R. That means I'm going to decrease F by a factor of 1/4. Right, because 1 over 2 squared, whatever I do to this side, I also have to do to this side. I've doubled this value. Because this value is squared, I have to change this 2 to a 4 because it's 2 squared. So I have a 1 over 4 that I also have to have over here. Because anything I do to this side in this relationship, I also have to do to this side. Okay? You ready for that? You'll have to do it on the test, I'm sure, to be able to look at those types of relationships. All right, two positive particles experience a force that is what? Attractive, repulsive, non-existent, or depends on the magnitude of the charges. All right, I'll stop at 28. 28. All right, good. Hey, this is a good one. Y'all are gonna love this one. Two cats are on a roof. Which one slides off first? And then you say, I don't know, which one? The one with the smaller mu. The one with the smaller mu. You get it because it's the coefficient of friction. If you have a smaller coefficient of friction, a smaller mu. But a cat says mu too. Mew. Sort of. I don't remember. I have a big list. All right, the electric field is a measure of the. I know you're gonna be telling your friends that today, right? Over lunch or wherever you go. The electric field is a measure of the blank per charge. What is electric field? All right, I'll stop at 20, at 30. I'll stop at 30. Okay, awesome. A is right. It is force per unit charge. So I don't have another one for you right now. Positive charge experiences a force in the what? The same, opposite, or does it experience a force in the perpendicular direction to the electric field? If I have an electric field, what is the direction of the force on a positive charge? All right, I'll stop at 33. 33. Okay, good. A is right. My positive charges will always move in the direction of the electric field, or at least they'll always experience a force in the direction of the electric field. And the units for electric potential are which of these? Joules, volts, newtons per coulomb are potages. Think about what is electric potential. All right, I'll stop at 33. 33. It's volts. And remember also that a volt is also equal to a joule per coulomb. So this refers to gravitational or energy. This refers to electric fields, and this is just something I made up. Bless you. And generally, objects move in a direction in which their potential energy does what? Does their potential energy increase, decrease, or remain the same? Just in general for objects in motion. They will tend to move so their potential energy increases, decreases, or remains the same. All right, I'll stop at 40. Stop at 40. Okay, good. B is right. Hey, what kind of ships do students ride in? Scholarships. That's cheesy, isn't it? Yeah, yeah. That's nothing like the cat joke. Okay, that was the cat one. That's also cheesy. Which of these must involve at least two charges in order to exist? The force, the field, the potential, or maybe all require two or more charges. I think if you can get this, you can sort of better understand the difference between force, field, and potential. All right, let's stop at 50. Let's stop at 50. All right, I'll stop at 55 then, or 58. Okay, we're all over the board. Yeah, there was a mad rush there at the end, but the right answer here is A. Now listen, the force has to have two particles, right? You can't just have one particle and it feel a force. But the field and the potential only need one charge, because they're not actually describing forces or energy. They're describing forces per unit charge or forces per unit energy. So I can have one force, or one charge rather, right here, and there be an electric field at this point. Now if I put a charge there, it will feel a force. So if I put a positive charge there, it will feel a force in that direction, in the same direction as the electric field, but it's not required for that charge to be there in order for the electric field to be there. Similarly, for the electric potential, if I have a positive charge here, I have a certain potential out at this point. Now, it turns out the potential is not a vector quantity. It doesn't have a direction. It can have a positive or a negative value that we'll get into later when we get into the neurons, but it doesn't have a direction. Like you might have heard of the resting potential or the membrane potential or the action potential. Those will have either positive or negative values, but they're not directions. They're just related to the energy. Now, the electric potential, if I put a charge here, it will have energy, but it doesn't have to be there for there to be a potential to be there. Okay? So forces require two charges or more, but fields and potentials do not. And we'll come back to this after we do capacitors. We have a few more minutes, so let's look at electric potential difference. We're going to sort of muddy it up just a little bit more because it's fairly important to think about potential, but then also potential difference. They're very similar, but when we talk about potential difference, we're talking about the difference in potential between 2 points. So this is measured in the same units. It's measured in volts, but the potential difference, which we're going to call delta V, is just equal to the difference in potential between 2 points. So let's say that I have a charge here. I have a certain potential here. I'll call this V2. I have a certain potential here. I'll call that V1. And so the potential difference is just going to be the difference in these two values. And that'll be important when we're talking about circuits. It's also pretty important when we're talking about cells, because charges will move across a potential difference because of their difference in energy. So they'll have different potentials between two different points, and we'll just describe that as a potential difference. Now, also, remember, potential is defined as U divided by Q, energy per charge. And so if I think of this in terms of a change in potential, that's going to be a change in energy over my charge. Remember this symbol, the delta symbol, it just means a change in. We used it for looking at velocity and stuff, like a change in time, a change in whatever. But here we're talking about a change in potential, which remember is an energy per charge. Says that if I have a change in potential, I have a change in energy, my energy per unit charge. Potential and energy are very similar. They're related. You just have that Q thrown in. Okay. Now let's begin looking at capacitance. We use capacitors for all sorts of reasons, capacitors in circuits. And we're not going to get that much into it, but I do want you to have a sort of a basic understanding of what a capacitor is, because it does become important in our body, in the way that our body works. I've already shown you roughly what a capacitor is, our capacitance. Capacitance, it's a device, a capacitor, is a device that separates positive and negative charges. That's how your book describes it. I think that's an okay way to think of it. Or you can think of it, too, as a device that stores positive and negative charges. And we talked about how we had two plates. On one of these plates, we'll have positive charges, and on the other plate, we'll have negative charges. So it does separate positive and negative charges, but it will also store those charges. So a capacitor is just a device that separates or stores these positive or negative charges. It typically consists of two metal plates. And often these are separated by an insulator. I'll show you a video next time where we'll take apart a capacitor. But it's just two metal plates that are separated by an insulator. So usually that's going to be a piece of paper. Serves a couple purposes. We'll talk about it next time, but I think we'll stop there. And we'll have a quiz on Tuesday, and then we'll see how far we get on this. But I'll let y'all know what to expect for the exam that following Tuesday. Okay? Have a great day. Have a good weekend, right? Yeah, have a good weekend.